1. Yeah. So, welcome. We're going to do a little example problem today. We'll chat a little bit about a review of this chapter. So we're in chapter 5 of the dynamic systems notes. Yeah, what's up? Yeah, you know what? I'm trying out this new software because the other software sucks. And you can't see my face, but I'm told it's there.
What if we have like a hard time hearing and get most of our like knowledge from facial and lip reading?
You're gonna have to really stretch yourself and look at my face and the screen. I know it's challenging. But,
I'm talking like when we watch the video.
oh, it should be on there when you watch the video.
Oh, cool.
Yeah. So yeah. I don't know. So we're doing this chapter 5, which is superposition, LTI system properties, etc. Right? And the lectures, there's not a ton of material in the chapter, but what we are covering is, first of all, that the principle of superposition is very important for linear time invariant systems, which is the vast majority of systems that we're going to be considering in this class. So we discussed how if you have an input, say U1, you put it into a system, and you got an output Y1, and then you said, okay, I'm going to put in 3 times U1 into the system. What should I expect to come out? And if it is, in fact, a linear system, then you will get 3y1 out. So if you scale the input, you just scale the output. Okay. Similarly, if you add one input, say u1 that you got y1 from, and another input, which we'll call u2, and you got y2 out, then if you wanted to know what happens if you put both inputs in at the same time, add them together, u1 plus u2, then what you would get out is actually just y1 plus y2. So that's principle of superposition. You can also split out the initial condition from the forced response. Okay, so if you find the initial condition, the response of the system to the initial conditions, which we call the free response, and you find the response of the system to the inputs separately, which we call the forced response, then you can simply add the free and forced responses together if you have a system where you have the initial condition being applied and the forcing function being applied. So you can just sum those up. So the principle of superposition is very, very helpful for solving these systems, these input-output representations of system dynamics. And it's a principle that applies throughout linear systems. So this is also applicable if you have a transfer function representation or if you have a state space representation. The same superposition principle applies. There's also the LTI system properties, the derivative and the integral properties that we discussed. And that idea is essentially if you have a linear time invariant system, if you have an input U1 and an output of that input Y1, then if you put in the time derivative of U1, you would get the time derivative of Y1 out. So differentiate the input, you just differentiate the output to find out what that response would be. Those are very useful properties. Superposition and the derivative property were used in the example in lecture 5.3, was it? That vibration table example. And we will do another example today in which we'll use that. Another thing we discussed was equilibrium and the stability of a system. And we found that the stability of a system can be defined in terms of its free response. And in fact, all you really need to know is what are the real parts of the roots of the characteristic equation. If those are all negative, we'll get decaying exponential terms, and we'll be decaying to equilibrium, and therefore the system is asymptotically stable. If we have positive roots, real parts of the roots of the characteristic equations, we will have increasing exponentials, and it'll never settle down to equilibrium. We call those systems unstable. And then those systems for which we have all stable roots, so all negative roots except for roots that show up with 0 real part in it, that would be a marginally stable system. So we talked about stability and how it comes down to the characteristic equation. And the example we did was pretty involved, right? I mean, we went through, it was a second order system, and we had pretty complicated solutions that we had to derive. I thought we would today do a simpler example with a first order system, and sort of to maybe nail some of these ideas home a little bit better, a little bit more thoroughly. So, and we're magically back, I think, hopefully, we don't know for sure. We're just making it up as we go here. So yeah, it does, but you know what happened is I have 1,000 things up here, and it gets too full, and so I can't see the little thing. When I'm on this screen resolution, because the only highest resolution I can get to on here is not very high. So yeah, it's weird. Anyways. Yeah, but believe. I mean, that one actually recorded. 7 minutes of recording happened. 7.5 minutes of what I'm assuming is just pure gold. So yeah. So let's actually solve this problem here. So we've got a first order system. Highest derivative is first derivative, y dot, plus ay. A is going to be some constant, some real constant here, a real number. And b is going to be another real number times u dot. So we're taking the time derivative of the input u, and c will be another constant, and that will multiply u, the input itself. So we have a derivative in the input. We have a derivative of the input in the forcing function, right? And we will make that input the unit step function, right? 0 until time equals 0, and then 1 forever thereafter. And then we'll have an initial condition. We'll get, real risky here by using lowercase d, but we'll use dot for time derivative in this problem, so d will not be derivative in this problem. Well, we love to live life on the edge in this class, so we'll do it. So we'll do part A here. We'll say solve for y of t for all time greater than or equal to 0 using superposition and LTI properties. So that's the first thing we'll do. That's actually the most significant portion of this problem, but I thought we would add a couple parts here. B, let's determine the steady state solution, if there is one. And C, comment on stability. Okay, so that'll be the problem we will solve. And we'll begin with, so all under, well, we'll start solving it saying 1, let's find the forced response for a simpler problem, okay? So let's solve for the forced response. For, let's say, instead of this whole forcing function, let's just take u. Let's just take this step input and make it the forcing function for a moment, okay? Y dot plus AY equals U. And we said forcing or forced response, therefore the initial conditions, or actually there's only one initial condition in this case, right? Initial condition will be 0. In other words, y of 0 equals 0 will be the initial condition we'll use to find the forced response. The forced response is always for when the initial condition is 0. Okay, so I don't need to say that explicitly. Once I say forced response, you should know initial conditions are 0. Okay, so we'll find this forced response. This forced response is a lot easier to find directly than this whole forced response, right? So we'll use superposition to find the entire forced response in a moment. Let's call it what we're looking for. Let's say y forced response. Let's do tilde on it, because the forced response of the entire thing is what happens when the input is included in this entire forcing function, right? So the tilde is the version that corresponds to this equation. Okay, so let's do that first. The first step, so we'll call it 1.1, is to find the homogeneous solution. Okay, the first step of that is to find the characteristic equation. Which is lambda, corresponding to the time derivative, plus a times 1. Okay, just a equals 0. What is the solution for lambda then? Negative a. So negative a is the single root of the characteristic equation that we get. And next we have the solution then. So the homogeneous solution is then, we'll call it y homogeneous, and yeah, we'll just call it y homogeneous equals k1. We're going to introduce a few constants in this problem. We'll call them all k with a subscript. So k1, e to the lambda t, as it always is, for a first order differential equation. And we have already, or we don't know what k1 is yet, but we have e to the negative a t for the lambda solution. We've got that. Okay, so we're ready now for the particular solution, right? 1.2. Particular solution, and we'll use our usual method of undetermined coefficients. So we'll guess a solution based on the form of the input. Form of the input is a step function, right? A unit step function. And we'll assume that a unit step function, as is the case, has a solution of, so y particular is going to be equal to a constant, k2. So we will have to determine what k2 is. If we cannot solve for a k2 that solves this problem, then we'll know that k2 is not a solution. But it will be, because I did this earlier, and it was a solution. So we'll plug it in then to our differential equation here. So what is the time derivative of a constant? 0. So I'll say inserting into, let's call this equation star. into star, we get 0 plus a times k2 equals the input after time equals 0 is going to be 1, right? And that's the solution we're looking for, is for all time greater than 0. So that input will be 1 because it's the unit step function. So that gives us a solution for k2 that is equal to 1 over a. So we have determined the coefficient for our particular solution. Therefore, the particular solution is equal to 1 over a. All right, 1.3. Let's do the general solution. So the general solution is always going to be yg equals the homogeneous solution plus the particular solution, right? So yh plus yp, and the homogeneous solution we found was k1 e to the negative at, and the particular solution we found was 1 over a. Notice that I've just been plugging in the constants as we've solved for them because they're pretty simple constants in this case. If the constants were not so simple, I would simply not plug in. Once I solve for the constant, I would leave it as the constant for the rest of the problem because it just gets really big otherwise. So this is our general solution, and we know what to do. So the forced response here that we're looking for, we actually need to apply the 0 initial condition to find it. So we have to apply that to the general solution to determine what k1 is. And so we will say specific solution. And what we do at this point then is say our initial condition is 0. So 0 equals this equation evaluated at time equals 0. So k1 e to the negative a0, right? E to the 0 plus 1 over a, which gives us a solution for k1, which is negative 1 over a. Okay. Good. So we have our specific solution. The specific solution is then this forced response that we're looking for. So it's this forced response to the simplified problem. So it has the tilde on it. And it's equal to negative 1 over a times e to the minus at plus 1 over a. We recognize that this could be easily simplified by factoring out 1 over a, so that we have 1 minus e to the minus at, and that's good. So we've got our forced solution to the just to the input, right? So this is what happens when we have an input of a unit step function. If our entire forcing function was just that input. But of course, we also have the rest of these terms. So we don't have the full forced response yet, because the forced response includes all of this as the forcing function. But this is where we're going to use the principle of superposition and the derivative property of LTI systems. So what we can do here is, in part 2, is solve for the entire forced response. So that's going to be that is the forced response thank you of y dot plus ay equals b u dot plus u. So we can say that superposition and the derivative property of LTI systems imply, in this case, that the output that we found, the forced response that we found here to the simpler problem, will form the forced response of this input to the entire system. So let's call that forced response just YFO for forced. Simply as this linear combination here. So YFO equals, we have this linear combination here, B times YFO dot, which follows this B times U dot. So we differentiated the input, we multiplied it by B, so we differentiate the output, we multiply it by B, plus the, this was a CU, right? There was a C there, CU, plus C times Y forced response. So if you multiply the input by C, multiply the output by C. If you add two components of the input together, you just add the two components of the output together. So that is superposition, and then this was the derivative property here, where if you differentiate the input, you can just differentiate the output. So let's sidebar over here, compute y for, oh, I needed to put the tildes here, right? Sorry, these were both the tilde ones for the simple problem. Y forced response tilde dot equals the y forced response tilde was equal to this, so we take the time derivative of that. This first term, a is a constant, this 1's a constant, this first term is 0. Second term, we've got an exponential, so I'll just write 0. And exponential, which is minus 1 over a. Chain rule applies to the exponential. Derivative of e to the x is e to the x, but then you have the chain rule. So we have the inner derivative here being negative a, right? So that will multiply negative a and e to the minus a t, which is equal to the negatives and the a's both effectively cancel, e to the minus a t. So we can just plug that in now. B, y forced dot, tilde dot, is e to the minus a t plus c times the entire forced response here, which, so put the 1 over a there, plus c over a times 1 minus e to the minus a t. Great. So this is our forced response. We've got it now. But we also have an initial condition. So we need to find the free response. Free response YFR. Which is to say, that is, solve, we have y dot plus ay equals 0. The free response is the response of the system to initial conditions and zero forcing, right? So with the non-zero initial condition, which was that y of 0 equals d, constant d. Okay. So we'll solve this, but the first step, of course, would be to find the homogeneous, well, it is a homogeneous equation, so to find the homogeneous solution, we have to find the characteristic equation, and that characteristic equation is the same exact characteristic equation that we found here, right? So this homogeneous solution is actually exactly what we need, again, but it has a new constant, because this K1 we found down here assuming 0 initial conditions, so we can't use K1 again. We can reuse the same form of the solution. So we'll say from the homogeneous solution above, which is in section 1.1, we can say that the homogeneous solution here is equal to some constant, K3 we're up to now, e to the minus a t. Now the particular solution when we have zero forcing is what? 0. The general solution then is just equal to the homogeneous solution. Therefore, we already have our general solution. So identify this as the general solution as well. Therefore, we're able to find the specific solution by applying the initial conditions, by applying the initial condition y of 0 equals d. So applying that initial condition, we say that d is equal to this equation with time equals 0. So K1 or K3 e to the minus a0, right? Or just e to the 0, which implies that our constant K3 is just equal to d. And we can realize that this is our free response then. This is our specific solution. Therefore, it is the free response. So therefore, y free is equal to d e to the minus a t. Great. So we now have a forced response and a free response, and we can use superposition again to find what the response is to both the initial conditions and the forcing, which we'll do in part 4. So total solution is by superposition. That it is just y equals the free response plus the forced response, which, just directly plugging in, are b, so this is the forced response, well, we'll do the free response first, d e to the minus at plus b e to the minus at plus c over a times 1 minus e to the minus at. So to simplify a little bit, we can collect all the e to the minus at terms. So we will say we've got a d plus b minus c over a times e to the minus at plus c over a. Okay, so this is the answer to part A, right? Great. I'll make this a little bit bigger so I will be able to add in the other two parts. Okay, so part 5 of our solution is to address B here. Determine the steady state solution. Well, looking at the result from A, we can see that this term is the transient, well, is going to be the determining factor for the transient response, right? So when this term remains significant, we'll still have a transient response. When this term is gone, or mostly gone, its effect is mostly gone because it's never going to quite be equal to 0 in finite time. We have the other term left, which is the steady state response. We could take the limit as time goes to infinity if we wanted to, but we can also just recognize that this entire term is going to go to 0 as time increases, so we'll be left with c over a. Y, we'll see steady state is equal to c over a. So that is part B. Sixth step in the solution is to consider the next question, which is to comment on stability. Now, stability, we discovered, is governed by the roots of the characteristic equation. We found the roots of the characteristic equation really quickly in this problem. So we could have actually commented on stability way back here in the third line of the solution. But we were interested in something else at the time. But now we can realize that we've already done the math that's required, which wasn't too involved. But all that's required now is to realize that the one root of our characteristic equation is negative a. So is negative a. So we can then say, therefore, if a is greater than 0, the system is stable, right? if a is less than 0, then the root becomes positive, right? And we have an exponential increase. So we'll be able to know that this is an unstable system. And if a is identically 0, then we have a response that doesn't change with time, but also doesn't go to an equilibrium either. So this is the marginal stability situation. The decay doesn't happen, so we have marginal. I should have underlined this one too. Marginally stable. Notice that our part 4 of the solution, part 5, we found the steady state solution. We assumed, we should have explicitly stated it. We assumed, what about A? Yeah, well, it has to be negative, right? Or sorry, positive. Right, because there's no steady state value if it's unstable, right? It never comes down to an equilibrium. Okay, so that's this problem. Are there any questions on this? Okay. Yeah.
When talking about the A value and being stable, in the notes there's some elements different. But is it like if the lambda value is less than 0, it's stable?
Yeah. Well, it's because lambda. So lambda and A are of opposite signs.
Oh.
Yeah. So that's why the reverse there. The other thing to let's see. There's something else that's going to comment on there. Yeah, so you have to make sure that, so we're talking about lambda. Oh, it's the real part also. These roots were real, right? Because A was real, so lambda is real. But if you have a quadratic equation, second order system, the characteristic equation is quadratic, and you can have an imaginary component, right? You can have a complex solution to the characteristic equation. And it's the real part, the sign of the real part that's important there. So in this case, there was only a real part, so that's all we considered. But it is the real part that is important for stability. Okay. You saw that in the previous example. We looked at that because it was a complex root, that example. Okay. All right.